Yeah, so like Archana mentioned, today we'll be talking about we'll be doing a paper reading where we'll read one or two papers. And then, and before we do that, we'll also kind of do a short tutorial on what a research paper is, how research papers are, written, what do they look like, and how you go about reading them and finding new research papers. Okay. So let's talk first before I start. Let's talk a bit about like what a research paper is. Um, a research paper is basically when a professor, so I like usually it's a professor or their students when they find something novel, when they work on something new, and they want to share it with people. They usually write it as a research paper and then they publish it. So that's like the standard like way in which like a research paper is like you have an idea, so and then you work on that idea, you get some results, and if the results you get are good, and if the results are something new or interesting, then that is when the professor and the students and all of the people who worked on that paper will who worked on it will write a paper, and then they will try to find like a conference to publish it in, or maybe a journal or something. The reason why it's important to read research papers, especially when you're working on edge computing, is because edge computing is a really fast moving field. And so what that means is there are a lot of professors and a lot of students and independent researchers, and even industrial researchers who are working on edge computing and constantly innovating and finding out new things. And the way and so these new things, they aren't really like released as, let's say, like a book or a course or a blog or something. They are almost always released as a research paper. So if you want to be updated in the field, and if you want to keep keep learning new things, the best way to do it is to read research papers. So what are the parts of a research paper? Research papers, like, depending on the conference or the journal, like someone submits it to, or even like people nowadays submit it to archive. Like papers can have different formats, right? So for instance, you might have like a single column format that looks like this, where everything is written in one column, or you may have like two columns, for instance, like this. There are also many different ways in which the title and the author name and other stuff like abstract and stuff will be formatted. So for instance, this is like left formatted. This is like the authors here are put in the middle. The title here is in bold, but here it is, and all of that. You'll have a lot of these things. But even though there are like going to be a lot of differences, most papers will still have a few things that are going to be common to them. And these are, like all papers will have a title, and that title will tell you what the paper is about. Right. And then after the title, you'll have like the authors and their affiliation. So for instance, here this paper, it has like 3 authors, and they're all from UC Davis. Over here, they're from all of the authors are from Google. So this just tells you with who worked on the research paper, and oftentimes the order in which the authors are written, oftentimes will tell you who worked on the paper, how much. So usually, like first authors have usually do more work, and like authors with the name at the end you usually have like a more of a an advisory role in the paper. But like that's not like oftentimes the case, that it's not like that. But sometimes it is. And yeah, finally you'll have like an abstract. So an abstract is one of the most important parts of the paper, because it tells you what the paper is about, why the author wrote the paper, and how they went about, doing the things that the paper is about, and the result. And the reason that the abstract is really important is because, like a paper might be like 10-20 pages long, right? But the abstract will almost always be like, just one paragraph, maybe two. And so the abstract is like a really short way to find out what the paper is about and the results that the authors got. And that's just like a really good way to find out if the paper is worth reading or not. Or maybe, even if it's a paper you read like maybe a long time ago, you can just reread the abstract, and it's a good way to remember what the paper what the paper was about. And finally, papers will have an introduction. And the introduction will be where, like the authors will lay down like the foundation of the problem that they are trying to solve. And then they'll tell you how what work they did to go about solving that problem. So the introduction is also sometimes really important, especially if you are reading a paper in an area that you are not really familiar with. So the introduction will help you get that foundational knowledge and the background knowledge that will help you understand the paper. Then the paper will have like other stuff, like stuff in the middle that will go more in detail about the work done. And that can vary from paper to paper. Different papers will write it in different ways, but at the end, papers will almost always contain two things, which is the conclusion. So the conclusion is basically like the abstract, but then in a way that it reveals everything. So the abstract could you might think of the abstract as kind of like a teaser for the paper. The conclusion is kind of like it'll just tell you everything that the authors did and just conclude their whole work. So the conclusion will also contain the what, why, how, and the result. But it might be a bit more detailed and a bit less like a bit less like a trailer or a teaser. It'll just be completely, it'll just give you the whole picture. And finally, you'll have some references. So, like over here, this paper had like 24 references, like maybe even more probably. But yeah, references are like other works that the authors had referred to while writing this paper. And it also is a good way to know about like the past work in this field and similar works in this field, in case you want to do like a review of a whole research area, right? So that's the abstract, intro, conclusion, and the references. And in between you'll have like, for instance, especially in deep learning and machine learning research papers, you'll have like an architecture diagram, for instance. Lots of papers have those. You'll also have results, which might be formatted in like a table like this, or like plots like this. And something that I personally really like reading are like discussions. So discussions might be like the authors will go into like more details about their work. They'll try to maybe give reasoning for why they're getting the results they're getting. And they might talk about some interesting results, and maybe like future work that they want to do in this area and stuff like that. So discussions are always like really interesting, especially to me. Yeah, so with that, like we've covered like what a research paper is, why it's written, and what it looks like. How do you go about actually reading a research paper? Because research papers, they're really dense. And when I started reading research papers, and I'm sure if anyone else has, and even Archana has, when you start reading research papers, especially like the first 2 or 3 papers, because these papers are so dense, you can barely get past, like one paragraph or 2 paragraphs. Because remember, research papers, right, they're not like books where you can read pages of them. Because a lot of papers are submitted to journals or conferences where there are page limits. So authors have to condense a lot of information in a really small space. And the way they do that is by using really complicated words, by, for instance, writing things, like trying to fit as much information as possible in a really small space. And so that makes papers really dense, and that makes papers really hard to read. And it doesn't get easier, to be honest, trying to read research papers. There are very few authors that I know that can actually write papers that are short and small, but at the same time that are really readable, like easy to read and easy to understand. That's a whole different skill altogether. Um, so how do you actually read a paper? So usually, because research, there are like so many research papers that are released, we usually don't read the whole paper. In fact, like, and I'll tell you two methods that we use. So method one is what Archana uses, and maybe she can go into more detail in after I explain. But what method one is, you read the title, and the title will tell you if the paper is relevant to what to the area that you want to do research in, or to the area that you are interested in, right? If if the title says something like, I don't know, how we took a picture of a black hole, right? As an edge computing researcher, that's irrelevant to me. I don't really want to know, unless I'm interested in that. But so I won't probably, so like, if I come across a paper with a title like that, I won't read it, right? But let's say the title is relevant. Then what we do is we read the abstract. And so by reading the abstract, it gives you more information about the paper, a bit more information. So it gives you more information to kind of decide if the paper is relevant or not. And also, if the paper, like the work done in the paper, is really good or interesting, right? And and so I just want to kind of say here that the title and abstract, it'll take you like, even if you're like a really slow reader or something, it'll take you 2-3 minutes to read it at most, right? And so within, just by spending 2 or 3 minutes, you can like just like get rid of like 90% of the papers, right? Because you'll just realize, just by reading the title and abstract, that either this work is not relevant, or this work is not interesting or good enough, that that it actually like warrants a read. And if you get and after that, that is when you read the like, or Archana prefers to like read the conclusion, to see if the results are actually good and if the work is actually interesting. Yeah, so Archana, like, did I miss anything? Is there anything you wanted to add to this?
Yeah, so one thing I definitely want to add is that, this is not a method set in stone. So just in case if you guys are wondering, like, is this the method? Is it something that is like a rule of thumb or something? Definitely not. Okay. So this is something that I have just sort of done over the years, where, for example, so how did this thing come into like practice, I should say, is that as Soham mentioned, right? Sorry, as Soham mentioned, we have like we end up reading papers, and then papers have a lot of references. So, for example, a really good research paper might easily refer to at least 20 to 30 papers, that I'm saying at a minimum. So, which means that it's not super necessary to go through references, but especially when you are writing a research paper, it's important to give references. That means you have to go through what other people refer to. It's like you almost can think of it as a chain rule, like you have to keep looking for papers in that point. So when that happens, you have to be a little quick about how you do it, and this is a quick way. So I wouldn't say it's like a really good way if you're looking to read the paper properly, if you're trying to really if this is a really good paper and the community said this is the paper. For example, you are reading I believe, like, when Jan LeCun wrote Lynette. So, when you're reading that paper, that's like the paper, right? I mean, you wouldn't skip parts of it. So, papers like that, I would definitely say that read all parts of it. But if you are reading papers which are not so, not so common, or, you just heard by word of mouth, or you have been just going over it previously, so then I would say try out this method.
Yeah, exactly. And you're right. I should have prefaced this by saying that This is a fast way to read papers. You definitely don't want to do this if you are reading something that you already know is interesting, or something that the community has like told you that that this is something you have to read, or something if you're reading for your work or something. This is just a way to kind of skim through a lot of papers really quickly and find out if the paper is good or not. So method two, which is something that I prefer, is, so I read the title and abstract first, because it tells me if the work is relevant and if it is interesting. Then I often read the introduction. This is so that I understand what the foundation of the work is and what the motivation for the work is, because oftentimes that's also important, especially if you feel that the research area is relevant to your field. You might want to know why the researchers went about solving this problem, or trying to tackle this problem. That is almost always present in the introduction. So that's why I prefer to read the introduction as well. And after that is when I read, look at the architecture diagram, and to kind of because the architecture diagram is like a really quick way to figure out like what the authors actually did. Um, and like what they built. So that's like, for me at least, that's a really quick way to just get a rough idea of what the authors did actually. And usually that's enough for me, like that, like by that time, like I know, like you'll know what most of the paper is about. And finally, if there's any discussions, like I said, I really like like when authors like discuss stuff in the paper. And so I often like read the discussions, just because they often have some interesting tidbits or results or comments, right? So for instance, I want to give an example, right? For instance, this is like a paper that was released recently called TAPNet, which does, which figures out like what you want to, like you can do gestures on your screen just by tapping at different positions, right? um, so yeah, interesting concept. The introduction tells me why they're doing it with and all. And then after that is when I just looked at the architecture diagram, and just by looking at this, like I figured out how they're doing multiple like how they are working on multitask learning, and like what kind of inputs they're using, what is their model architecture, what they are like how they're training their network and so on. I can tell all of that just by looking at the architecture diagram, right? And then I just saw like the results that look like this, and they had a discussion section, so I read that. And this paper, it's not like really groundbreaking research or something. I mean, it's really interesting research and it's really good work, but it's not going to, it's an application, and it's not going to, like, for instance, change the direction of the field, right? So for me, as someone who works in edge computing and read this, I just read it just to know the work they did, and in case I come across a problem where I have to do something similar, then I'll remember, hey, like this paper did that, and then I would go and read it in more detail. But just for just to when you see a research paper and you just want to know what it's about, that's like a really good way to do it. Yeah. So yeah. And now I want to like do some, like, tell something that is a bit controversial, and and of course, like, these stats, like 80%, 15% and all, they're not set in stone. That's just something that I came up with and sorry, off the top of my head. But basically, about 80% of the research papers that you will find will not have, will not have done anything interesting, or will not have done anything relevant, right? So that's like 80% of the papers. You can just like read only the title and abstract and then just forget about it. After that, like another 15% of papers, you can just skim through them. You can just, maybe read the abstract and the conclusion, maybe look at the architecture diagram, and then, like, be done with it. Some papers, about 3-4% of papers will have really good results or discussions. So you might want to read that part. And there will be very few papers that you will want to read completely. Papers like, for instance, like Archana mentioned, like the first paper that talked about CNNs. That's something you would want to read completely. Or maybe like the paper that talked about self-attention and transformers. That's one you would want to read completely. But that's going to be like very, very few papers, right? Okay, so I know I talked a lot. Let's kind of find, like, I just want to like wrap this up by telling you how to find good research papers. And there's basically two ways to find research papers. You can either find them based on topics or based on authors. And I'll talk a bit about which one you should do and which one is good and all. So if you want to search a paper by topic, then it's like by searching a paper by topic, it's really good because it tells you, everything that's going on in a field, right? And the topic can be like really broad, then that'll give you like a lot of papers, or it can be really narrow. So for instance, a broad topic would be something like, I don't know, deep learning. That's really broad, and you'll get lots of papers with lots of stuff, right? A more narrower topic might be something like edge computing. And so that'll give you less papers to see. But yeah, so for instance, for topic, like how do you find papers? So you can follow Twitter accounts and hashtags. That's, in my opinion, the best way to find good, interesting papers. You can also find papers by topic on archive. Some conferences, for instance, are have topic restrictions. Like that's a good way to find papers by topics that and if it's a good conference like NeurIPS or ICML or something, then chances are you might not need to like do a lot of vetting of the paper or something. You can just go ahead and read them, right? Google Scholar is also a good way to find research papers by topics, and you can also follow research labs. That could be like in a university or even in like industry, like for instance Google Brain or DeepMind or something. So for instance, in like these examples are for edge computing. Edge Impulse is a really good Twitter channel to follow, so you can do that. Hashtag TinyML on Twitter is also really good. There's also a TinyML conference, and as far as I know, it's the only conference that is focused on TinyML. So you can take a look at that. And yeah, there's also another conference called ISSCC, and they also have a YouTube channel. So this conference is more about hardware as compared to like just edge computing, but they do have a lot of edge computing papers as well. And finally, there's like the MIT WCS lab, which is like a really good lab for tiny, like, and they do a lot of work in edge computing and tiny ML. The only disadvantage for finding papers by topics is that it can be really overwhelming. If you just search for papers on edge computing on, let's say, Scholar or Archive, you'll get like hundreds of results, right? And it can be really overwhelming. So it's always good to follow like certain people on Twitter or certain hashtags, or just follow some conferences, because it'll be like the searches will be more narrow. And that those are going to be like top tier papers, right? And the other way is to find papers by author, and this is good because oftentimes authors only work in niche areas, in fields, and so it's really good for filtering papers. And you can follow authors on Twitter, or you can follow them on Scholar. You can also follow an author's lab, especially if they're a professor or something. And some people also have blogs, and you can follow them, follow the blogs as well. Another good thing about following authors on Twitter is they will also often share other work that is not theirs, but like similar work in their field. And that's also a really good way to find papers. And the rule that I said before, right, like 80-15 4 and 1% of papers and all, that is also that also applies here. Like even if you follow like a really good conference, even then a lot of papers will be irrelevant, or they won't have like really good, interesting results on something. So yeah. So that rule applies there as well. So some people you might consider following: Sarah Hooker, who is one of my favorite researchers, and she does a lot of really good work. And in fact, like two of the papers we'll be sharing today are actually written by her. So just to like kind of go on a tangent and talk a bit about her, because like I really like her work. A lot of researchers, what you will find is they'll like just release a lot of papers. They might release like one paper a week or something. And what happens when you release a lot of papers is, like oftentimes the work will not really be that good. Right, they'll only release a few really good work. So out of like 10 papers, they might just release one really good paper. But the good thing about Sarah Hooker is when she releases a paper, and she doesn't release too often, the work that she does is actually really interesting, and the results that she gets are also often really interesting. So that's why, like, I tend to follow her a lot on Twitter and Scholar, and follow her work a lot. Another person who is Pete Warden, who is not really a researcher, but he writes really good blogs, and shares a lot of good work on Twitter as well. And Pete Warden, personally, is someone who inspired me to work on edge computing. And so yeah, so I would recommend you follow him as well. Song Han and Vivian C are both, if I'm not wrong, are both from the MIT EECS lab, and they are also really good researchers. Vivian C, for instance, has a really good paper, like a review paper on edge computing and TinyML. It's a bit old. I think it was released in 2017. But even though it's old, the work is still relevant. Maybe I can share that paper later on. Yeah. But the problem with following authors is that authors often tend to work in like some really niche areas, and so it's if you just follow authors, it's often very difficult to know the other stuff that is happening in the field. So what I would suggest is like do a bit of both. Follow some authors, follow some topics, read papers in both, and that's a good way to get like a lot of research ideas, and read a lot of really good papers. Okay, so before I start with the paper, and the paper we'll be reading is The Hardware Lottery by Sarah Hooker. Are there any questions? Archana, maybe you wanted to add something?
So we had a few questions, but I guess most of them were answered. As to the good authors, you already answered. So yeah. But let us take the other questions. Can you give some URLs for some labs that we can follow? I'm trying to send you the MIT lab.
Yeah, MIT EECS is it's a really good lab. Let's see, are there any other labs? So I can't really recall any other labs that I follow personally. I mean, I know a lot of other labs that work in the field of edge computing, but like none that I follow, because they tend to release like that they tend to do a lot of work. So most of the work is irrelevant for me. But yeah, MIT ECS is like a really good lab. And if you follow Edge Impulse, they might tweet out work done by some labs, and then you can follow those labs.
Exactly, yeah. That's another good advice, that do follow Edge Impulse, because they tweet out a lot of good papers, and usually they're papers that are really good for edge computing, the very least. So that is something I would definitely recommend.
Yeah, like the tablet paper, right?
Yeah, exactly.
Yeah,
So
I
maybe
wouldn't.
not a lab.
Yeah.
But there are other papers that Edge Impulse does release, like not release in the sense, but they do tweet it out, and we talk about a lot of hardware-based papers. But what I wanted to say is that they're not a lab, they're a company, but nevertheless, the papers, they do release a lot of papers. Okay, another thing that was asked is, so Sheshu wants to know how many papers do we read every per week or month?
Yeah. So when I was like a master student, like up until like 6-7 months ago, I would have been reading So let me define reading, right? I would skim over at least 3 or 4 papers a day, right? Like not read them, just see the work they did, see if it's relevant, maybe look at the architecture diagram and stuff like that. So 3-4 papers a day. And for my work, I would read I don't know, one paper, or maybe like, let me say, like on a weekly basis would be something like 3 or 4 papers on a weekly basis. Sometimes I would have to reread papers because, I would be implementing them or I would be using their work. And so that would mean I would have to reread the paper multiple times to kind of really understand it, right? Um,
Yep.
so yeah, I would say like it's a combi it's like I personally I would consider like even skimming through a paper like reading it. So then yeah, probably like 20 papers a week. But that's because I was a research student. Currently, right now I'm working in the industry and stuff, so I don't really have a lot of time to read. So I read probably 2-3 papers a week. um, so right now I'm more selective about the papers I read because I have less time. So I only read a paper only if it's like, like people are really talking about it in the community, and all, only then. Yeah. What about
Yeah.
you?
Yeah, and one more thing that I wanted to add here was like take a segue here and also talk about the fact that every 2 weeks we read a paper with Edge Impulse and the team at Edge Impulse and also invite other people. So if just in case you're interested to, for example, do like a paper reading or even like be a part of paper reading, you can let us know. So I can drop you the link. So they host Twitter Spaces. I don't know if you guys have used it. It's supposed to be similar to Clubhouse, but it's available for all devices, Android and iOS. And so they host it at 11 a.m. EST on every Thursday. And yeah, sure, I can. So you can do one thing. You can join in on. You can just follow Edge Impulse on Twitter. So the thing with Twitter Spaces is they can only release the link like 5 minutes before the event. It doesn't get released beforehand. So I'm sorry, there's no invite link per se. But if you follow Edge Impulse, you can get the link because the moment they start the session, like 5 minutes before, they start tweeting it out. So you can join in on the session. It's one is happening this week actually. We haven't yet decided on the paper, like we're debating between 2 papers, but do join in. We'll be going through one of the papers for sure.
Yeah.
So yeah,
Yeah.
we had one more question, but I think we should jump right in because I know we are running short of time and we can come back to it. So
Mhm.
again, guys, feel free to ask questions. We're going through 2 papers today. Really quickly, we'll be going through, we'll just be going over like our top level pieces, but I really hope you can ask us questions. And, the only way we can learn here is by you asking us questions. So please don't be shy, ask. And that way, both, all of us can learn, and probably something that you are wanting to ask, people are too. So don't be hesitant, go ahead and do ask.
Yeah.
So, yeah.
Yeah. Okay. Yeah. So, okay. So I wanted to talk about this paper called Hardware Lottery. And this is in some ways a really good first paper to read and also a really bad first paper. So really good first paper because this is like a really easy paper to understand. It's not really that dense. It's really well written. But at the same time, this paper is kind of like an opinion paper, or like kind of like yeah, it's like an opinion paper. So it doesn't really have any results, or it doesn't really have any like architecture diagram or something like that. It's just like a essay, an opinion essay, but nevertheless it's a really good paper. So let's just take a look at forget this, let's just take a look at the title and the abstract, right? So I'll give you like 1 minute to read the abstract. um,
Yeah, I also dropped the link to the paper just in case you're maybe viewing via your phone or something. You can click on the link and look at the paper. I
yeah.
dropped it onto the chat.
Yeah. So just by reading the abstract, right, you can tell that what the author is talking about here is that, hardware, software, and algorithms, people think that they are separate, but in reality, they kind of interact with each other, right? And this interaction, especially, is what causes some research ideas to kind of become more superior and to essentially like win or be more popular as compared to other research papers. And so research papers like kind of win or become popular simply because there is kind of like a good connection or synergy between this domain of hardware, software, and algorithms, right? And like finally, Sarah Hooker says that like she'll be talking more about this hypothesis or this opinion throughout the rest of the paper. So you can get like just all that information just by reading the abstract, and just by reading that much, you can um, it's a really good way to know if this is something that interests you and if you want to read the whole thing, right? But before we move on and talk about the rest, I have a question, which is, do you think that this hypothesis or this opinion is true? Do you think that there are cases where the hardware and software and algorithms actually caused a research idea to win? Or do you think that that's not the case, and do you think ideas win or become more popular simply due to their own merit? Yeah, what do you think? If you want to raise your hand, and then Archana can let you speak.
Yeah, yeah,
Yeah.
please do. Guys, please do raise your hand, and that'll be great if you guys want, go ahead and want to, chime in here. And again, please don't feel shy. It's like one of the advantages of having like an online meeting is that you can come on and talk, and don't need to worry as such. So yeah, did anyone raise up? So guys, again, please do raise your hand and let us know. I mean, it's a very interesting question, right? It's something that we are sort of going through almost every day. It's something that we face every day because, we might make, like, have some algorithms that are supposed to be really great, but the hardware is limiting. It's not able to take care of it. So, I mean, we have issues like that. On the other hand, it can be also that, the hardware is really advanced, although I've heard less cases of that happening. The hardware is really advanced. Hi. Hi, Joanna.
So Joanna and I think Renju wanted to talk, so I'm just like allowing them to talk.
Sure. Sure, sure. Hi,
Oh,
guys.
no, I'm sorry. I was just saying yes to the question. Um,
Okay, okay. No worries. But you can let us know if you have any opinions or you've like faced a scenario where you felt like the hardware was really good or the hardware was really bad, but the thing that I made or the algorithm I had was supposed to be really fast, but the hardware couldn't catch up. If you had cases like that happen, do let us know. And yeah, so shall we move ahead?
Yeah, sure. I just wanted to check if Renju wanted to say something.
Yeah, this Ranju here. Okay, I'll just talk, okay? Because
Sure.
when I initially started with neural networks, right? So, when you time to tune your models, it takes time and time and time. So that time, when you come from your, because I initially worked in the machine, this assembly language, so it was so quick and fast. Okay, when you come to here, it's like take ages to do it. So that
Yep.
time I really felt that, the hardwares are actually making our life more miserable.
Yeah, and it's funny you should say that because we'll talk a bit about that as well in some time.
Yeah,
Uh,
but I
Okay.
think you hit right at the like the nail right at the hammer or whatever the phrase is. But yeah, you hit right at the right spot talking about the fact that the hardware hasn't caught up, and that's something that Sarah Hooker actually brings up. So this paper is, if you haven't read it yet, I would definitely recommend because it's almost like a blog, so you can feel yourself agreeing to what she said.
mhm.
Okay. Okay. Thanks. We'll do that.
So after that, like, the paper has an introduction. And what the introduction talks about is that, there's this bias in research. And that bias is that research ideas have a dependence on the hardware and tools and stuff. Um, and so because research ideas depend on this synergy between hardware, software, and algorithms, there is like some noise or some bias in research, and also there is inertia, or there is something stopping you from actually from researchers from recognizing promising research areas, right? And so it's our tools that actually causes a bias and an inertia of research areas. So even though the paper is titled hardware lottery, it's actually not just hardware, but it's kind of like a combination of all the domains that causes some ideas to become more popular than others, and that is what the lottery is. So let's talk about these domains one by one. The first one is hardware. So as someone who personally would like worked as a hardware, like worked in building actual like CPUs and chips, I know how hard and risky and difficult and like how slow building hardware actually is. It took us, for instance, about 1.5 years to build like this very simple, very small chip. So it's slow. So even if you've built it, even if you've like worked on it, like have all the code and all the stuff ready, you then send it out to a manufacturer to actually print the hardware on a die, and that process itself can take anywhere from 6 months to, like, I don't know, 2 years as well in some cases. So building hardware is slow. Building hardware is also risky as well, because it takes 2-3 years to get your hardware back. The field might have already progressed in that time, right? So it might not be, so the work you have done may not be the state of the art anymore. So hardware, building hardware is also very risky. And finally, it's also very costly, like costly in terms of manpower and time needed, and costly in terms of just like actually like submitting the chip to be manufactured. And finally, it's extremely difficult. You need a lot of really good people working together in sync to try to build like a chip. So yeah, so that's the preface, right? Building hardware is slow, risky, costly, and difficult. So with that, let's actually take a look at the timeline of how hardware was built. So at first, when computers were first built, like for instance, Charles Babbage's machine, it was actually like, a these were like single purpose hardware, right? They were like meant to be built once to do some purpose, and or to do like some kind of work, and then that's it. They just do that for the rest of their, like from then on. And so this is all before 1970s, by the way. And the reason for that is because these hardware were like it was really hard to build general purpose hardware at the time. And so people would just build single purpose hardware, and even like general purpose hardware, like for instance handlooms, right? These were handlooms were also machines. They were very hard to like program, like again, like reprogram them. So people generally would just program them once and then let it run. But after the 1917s, something interesting happened, which is like, we invented ICs, we invented the transistors and started building chips. And so now we could build general purpose hardwares and CPUs. The reason for that is because of something that a lot of us are familiar with, which is Moore's law, which basically says that every 2 years or about 1.5 years, we can like double the number of transistors on a chip of the same size. And what that essentially means is that every 2 years, your performance will double. And so at that time, building general purpose chips became like a no-brainer and became like non-risky, because that if you build something for your general purpose hardware, it's going to be, really fast, and the performance is going to be really good, and no, like in just 2 years time, right? So it doesn't make sense to build specialized hardware at that point, because you don't know if the performance 2 years later, like of your specialized hardware, if it will be better or not. So this time from like 1970s to about early 2000s was this time of general purpose CPUs, right? And then after that, Moore's law started kind of slowing down, and there's another thing called Dennard scaling, which is like how much power you can put into the chip, like kind of like that. All of these laws started like like collapsing, and performance improvements were not that well from the early 2000s, and like about 2010 and stuff. Um, and so it was at that point that people started building more specialized hardware, because like it wasn't because it started becoming more risky to build general purpose hardware, because you wouldn't know if the performance will actually improve or not, right? And so people started focusing on more specialized hardware, like for instance edge TPUs and VPUs, like the neural compute stick. But yeah, for all of these above, like all of these different times, the choice of hardware, or the hardware lottery, right? It was based basically on like less risk and less cost. Um, so whichever was less risky and less costly, that is what the hardware developers built. So how does this actually affect like some other stuff? So for instance, like what happened was, GPUs, right? The idea of GPUs were actually introduced in 1970s, but no one would actually use them for neural networks and stuff, simply because CPUs were kept getting faster and faster, and like no one would, and it did not make sense to use like GPUs at all, right? And like many other research ideas were not winning, because they might not have been fast enough on CPUs, which have some disadvantages. For instance, like one of which is like CPUs can do only one task at a time, and like other hardware like GPUs, which can do a lot of tasks at the same time. Right. So because CPUs were not like that suitable for doing neural networks, the popularity of CPUs in the 70s, 80s, 90s, and early 2000s, they weren't there, because CPUs were not suited for neural networks, right? And so during that time, other ideas, like for instance symbolic AI, which was suited for CPUs, they were more popular. More recently, we talked about pruning, right? And we talked about how pruning isn't really that efficient on hardware. So more recently, CPUs and GPUs, right? The way that they are built, they're not really good at executing pruned networks really quickly. And so you don't see the performance advantages of running pruned networks. And so, and so that's like also another hardware lottery. Even though right now more GPUs and CPUs are actually supporting pruned operations, but until a few years ago, like it wasn't there, and so the hardware lottery was against pruned networks. And even now, right, maybe there are other ideas, for instance, like graph neural networks, which may not be winning right now, simply because they are not really suited for our hardware, right? So we have a question here, which is, have you encountered, like have you come across a situation where you were working on something that you tried to run on your hardware, but it wouldn't run well enough, and because it wasn't suited? So what did you do in a situation like this? If you want to talk about it, just put it in the chat. Maybe we'll because we're running a bit short on time, maybe we can take it up in some time. Yeah.
Joanne here has one, but she did put it up on the chat. But Joanne, if you want to talk about it, you can talk really quickly if you want to.
Mhm.
It was just while I was in my boot camp, they have an auto grader system, and in order to run our models, we had to limit it to just a basic. So we had to uncomment our actual model and just run a basic model through the auto grader, and then somebody, an actual human, would look back on it and see our actual model that we built. But they only had one worker, so on their auto grader system. So we had to take into account for the hardware restrictions in that situation.
Yeah, that's actually really interesting. Yeah.
Yeah, I think we can
Mhm.
go ahead. But yeah, thanks, Joanne, for giving such an interesting thing.
Yeah, so the next thing is like, we talked about hardware. What about software and algorithms? So in the 1990s and in this general purpose area time, right? The programming languages that were more common was, like Lisp and Prolog. And these were not suited for deep learning. And they were more suited for doing like logic expressions and for solving symbolic AI stuff. And so that's also another reason why neural networks were not popular at this time, even though they were actually invented, and we had like all the algorithms and stuff were already there. uh, they were just we just did not have the technology to execute them fast enough to actually like see the performance like improvements by given by neural networks. Even though other languages like C++ and MATLAB was there, they were really not that popular in the deep learning community. So that's also another reason. And yeah, finally, even right now, like I was mentioning before, like compression and pruning, it's not really well, it's supported well by software, but not by hardware. Um, and so we don't really see the performance improvements. But now we are at this crossroads where uh, pruning and compression has been around long enough that hardware researchers and in general like hardware developers have seen the advantages and of pruning, and they're now slowly trying supporting pruning in their hardware. So for instance, the new NVIDIA GPUs, the 3000 series GPUs, they actually support some form of structured pruning, which is really great. And this also begs the question, like other algorithms, like let's say for instance capsule networks, which were released like by Hinton himself, who these are actually like difficult to train and execute efficiently with our current software and hardware stack, and so maybe that's why they're not that popular. We don't know, but that could be like one of the reasons why we don't actually see capsule networks being used to that often, even though in a lot of cases they have shown to like they do have better results. Yeah. So what about the future? um, like where do we go from here? So the future is that hardware development is still going to be expensive. So hardware developers will kind of want to stick to the beaten path and build hardware that is non-risky. And so they will only work on building or supporting hardware that is work on supporting software that is that we know will will work well. Um, and so we'll continue. So the gap will continue to kind of increase between hardware and software. And the only way to kind of fix that is to have more funding for hardware development. In terms of software, one way we could do is like build domain specific code that is very efficient on only some on like on a subdomain of research, because but again, like that's not really a good solution because that's also going to be really hard to build. And finally, we could tune our software so that it works better on hardware, which is already something that a lot of people are working on right now. Um, but yeah, that's also something else that we can do. Yeah, so I guess that's it for me. Archana, do you have any other thoughts, or are there any questions?
So I guess we had like two questions here.
Mm-hmm.
But shall we take it after the session? I just want to quickly go over the bias paper too, because I know that's like more of a research paper and it falls under the research paper category as such. But I want to know if you guys are comfortable with going maybe another 20 minutes into the session. If not, let me know. But I'll go over the paper and some aspects of it, which will be common with most other deep learning papers or edge computing papers that you might read. Okay. Let me go ahead and share my screen. Can
Yeah.
you stop sharing, sir? Okay, let me go ahead and share my screen. Okay. So, one moment. I hope you guys can see my screen. You can see my screen, right?
Yes.
Okay, so characterizing bias in compressed models. So do drop the link to the paper onto the chat so that people can check it out. So this is a paper, another paper, but I will not be, going over the steps exactly as Soham said, going step by step, but this will look similar to other deep learning papers you have read. This is another paper by Sarah Hooker and some other folks from Google Research. Also a really interesting paper about understanding bias that exist in compressed models. Now, compressed models are a lot more common when it comes to edge computing. We have, as we have seen, pruned models, quantized models, and other forms of compressed models that exist. But today, what we want to, look into is that, so we know that pruning like disproportionately impacts, when you look at the abstract, especially of the paper, what here it states is that pruning disproportionately impacts performance on underrepresented features, so, which often coincides with consideration of fairness. I know the sentence sounds complicated. What in short it means is that oftentimes when you compress models, there are certain features of the data which are something which are not talked about at all, and which end up you know uh, being disproportionate or end up having a bias in them. So that is something that this paper specifically looks into. Okay, what happens to these features? And they're going to pick up a very interesting data set and going to look into some of these features. Now, one thing which is very important here is that when you look at the features here, they might not be the classes that you're actually training it on, which means something like, so for example, someone said cancer detection. So for cancer detection, maybe you have like a binary classification model. So whether you're detecting if there is a tumor which exists or not, if not, you can also have like a classification model wherein you're determining which type of tumor it is. So those are classes in which you're training your network on. But there are other features, like for example, tumor size, tumor width, or other features like maybe roughness, or the way that the tumor looks. There's some features that we do not know about the tumor, or we do not entirely classify it on. But these are features that nevertheless exist on the data set. So those are something that we are looking into. Another way that you can look at it maybe is like, for example, not taking tumor because that's something that is not our area of expertise, is for example, you're training a data model on determining the type of dog. For example, you have like a beagle or a labrador or a golden retriever, and now you're trying to wonder if but you can determine what they are by the way they look. But another way to another set of features that the dogs might have is the type of ears. Is it like a very long ear? So that might tend to be a golden retriever versus maybe a shorter ear dog, like maybe a Doberman or something. So I mean, yeah, so that depends on how those are the set of features which the model has not been trained on, but nevertheless exist. The dog's ears, the way, the mouth of the dog or something. So those are the things that, it is not trained on per se, but they are underrepresented features as such. And we want to know how those underrepresented features are affected when we compress the model. So let me move on. So that is the question that they are asking today. Does compression amplify? Compression here means we are reducing the model size. Does it amplify algorithm, this sort of bias that exists in algorithms? So discussion is basically around relative merits of different compression methods, which are centered around the trade-off between the level of compression and the top line metrics like top 1 and top 5 accuracy. So this is based on previous work which was done by Sarah Hooker. That have found that critical changes in generalization between pruned and unpruned, which oftentimes happens, right? You want your model to be as generalized as possible, but what they found out was that there is a critical change, or a change which is definitely noted between a pruned and non-pruned model. So one of the interesting things here is introduce the CIE, which is compression identified exemplars. So you can probably consider it to be a metric or a parameter. But what I want to talk about here is something which is very interesting. Is the fact that, this compression identified exemplars as such is like a parameter that the paper introduces. Again, it's a little bit of math, but what you need to understand here is that today I'll not get into the math too much, don't worry. But what is the main takeaway, or what is something that you need to understand at this point, is that a lot of machine learning or deep learning papers will talk about metrics, will talk about parameters, or might introduce one of their own. So this is one of those papers which have introduced. I should have talked about bias first. So I will give examples later on, but for example, what is bias? So we have been seeing a lot of facial recognition systems, for example, which might end up, which might be sort of disadvantaged to a certain community or certain people of color. Why does that happen? Maybe the model that was trained for the facial recognition was not trained well, or maybe the data that they took in, the data that the model was trained on, did not have people like, equal classes. Was there an imbalance of class that existed? So that is when a bias is introduced into the system, that the model is now biased. It's going to start predicting more of one of the class versus the others. And that's what we want to prevent. And that is something we want to be talking today, that is bias as such, just in case you might hear me again and again talking about bias and might not know what is the context in terms of deep learning. So yeah, so compression identified exemplars are, it's defined as minimal changes to overall accuracy to hide disproportionately high errors in small subset of examples. Another line here which has a lot of things in it, but let us look at, what does it really mean. So when we look at compressed models, like for example, pruned or quantized models versus non-compressed models, it means that, okay, if a compressed model has predicted a certain label, looked at a certain label and said, okay, it's label X, and gave a prediction X, you would consider the non-compressed model also to give the prediction X. But what if the non-compressed model gives a prediction of Y? At that very point, you have like a divergence situation, or the one model diverges from the other in terms of the results, and that is exactly what we call CIE, and that is the metric that is being used whenever we notice this differentiation between compressed and non-compressed models, that the compressed model should have predicted a certain value, and the non-compressed model also should have predicted that value, but it isn't. At that very point, that is called CIE, and that is what they'll be calculating over and over again. So in essential, it determines model behavior, right? It should have done it, but it shouldn't. So it's something determines a model behavior when you're presented with a subset of data which is atypical. Again, which is atypical means the model did not really was not really trained on it. It does not mean that the model was trained on X versus Y. or was trained on the class X, it means it was an attribute, considered to be like the ear thing, right, for the dog. So in essential, what they're trying to say is that CIE is a way to audit these protected attributes in data sets. Now, I might be talking about dogs, and you might be wondering, like, how does it translate? So just stay tuned. In another couple of slides, I'll go through the data set they took in, and the data set they took in are like much more real world and much more of importance to us. So one of the biggest bottlenecks, we know that the larger the data sets of the modern data sets get, or the larger the size of the modern data set, the more is the cost for annotating or labeling each feature. So many real world data sets we have like labels for protected attributes are oftentimes not available. Like for example, I've also been talking about this. For example, if we do something for work, I don't know how many times did you find out the labels that exist of these protected class. What I mean by that is, like, you obviously trained it on certain classes, but did you also try and find out what were the labels for these protected attributes? So the paper basically shows CIE to be a way to automatically surface more challenging examples and over indices on these protected attributes, which are sort of disproportionately impacted. That's the takeaway at the end of the day, that, by compression, we are disproportionately impacting, or there is a bias that exists. So you could consider the word that disproportionately impacted means bias. And CIE is an unsupervised protocol for auditing, and it's given that the methodology is sort of agnostic to the presence of attribute label. It allows to audit multiple attributes at once, and hence it's like you could consider it to be like a valuable human in the loop auditing tool, right? Because you need to still go in and see if it did audit right. So it is human in the loop. Something that another is a good takeaway is that even though they're suggesting this, they're saying it's a human in the loops, which means that at the end of the day, you do need a bit of human supervision as such. So what are the examples of unidentified attributes in a data set? Okay, so prevalence of undesirable biases in machine learning data set. So yeah, so one is like, if, as I told you before, so when we look at facial analysis data set, we notice disparate treatment of darker skin tone due to underrepresentation. I mean, look, you could look at bias in an ethical way. Obviously, it's a ethics problem, but it's also a data problem, right? It's about how you collect data. So it depends which sort of data do you collect, and if there is an underrepresentation of a certain type of data that exists, if you look at it purely from the data perspective. Another way is that object detection data set tend to underrepresent images from lower income and non-Western regions. And then word co-occurrences. So another thing which is interesting here, which is actually associated with NLP, is that word co-occurrences within text data frequently reflect social biases relating to gender, race, and disability. So that is like an NLP-based bias or a text-based bias you could consider. So yeah, which brings me to the crux of what they did. So they took this data set, which is called Celeb A. It's supposed to be this data set of celebrity faces, annotated with 40 binary face attributes. I don't know if you notice any famous celebrities. I tried to notice one, but I think it was wrong. But if you don't notice any famous celebrity here, do let me know. Maybe just, put it up on the chat and let me know if you can spot any. But yeah, they're supposed to be like entire celebrity faces, but these are the ones that were, pictured in the paper. Obviously, they took the entire data set into account. And basically, this is what it's actually trained on, the class that it is actually trained on. It's supposed to be like a binary label, whether it's indicating if the person has a blonde hair attributes or not. So if they have like a blonde hair present, so then, it's a binary classifier that says yes. So yeah, that's like a, 1-0, you could consider it, right? So it's a binary label. If a blonde hair is present, great. If not, it doesn't detect. That's it. But now we are also taking in protected class. That's the important part here, right? These protected attributes. So the protected attributes are these protected demographic labels. And what are the labels that they considered? So the labels that they consider is, male, male, not male, old, not old. So there are 4 attributes they consider. And these are protected attributes again. So the methodology here is that they have two protected attributes, which are male and young. So male, young, you could consider it to be not old. They have also said it as not old, but yeah. So that is what they're trying to find out. And they have like an intersection between this. So they have male and young. Then there's an intersectional attribute, young male. So they're trying to detect or sort of figure out if there is bias towards this particular attribute. And there are other age and gender groups, as I said. There's male, not male, which they are represented as F, M and F, which I'll show on later on, and then old and young, or old and not old, you could consider. Then they have a subgroup error rate. Like, how do they find out if there's an error that exists, or a, if there is a bias that exists? They try a false positive rate, and they also find out a false negative rate, basically between the baseline and the compressed models. And they use three compression techniques. They firstly use pruning, which they do during training. They do fixed point 8-bit quantization. This is post training. And they do hybrid 8-bit with dynamic range, which is again post training. So these are the types of compression they try. So one another important thing here is that like you will again find these these things very common in other papers too, wherein they'll explain what they do to the model, right? This is important as part of architecture, as Soham explained. You will have pruning, pruning, and then quantization, and so on. So I mean compression here, but it might be something else in a normal deep learning paper as well. So yeah, and one thing which is very common with all papers, as we know, is that which model they're training it on. So they're using something called ResNet 18, which is also sort of a compressed model. It's not like your ResNet 50 or above. And it's Celid A for 10,000 steps with a batch size of 256. So yeah, so this is another important information they give here. It's important in the sense that you'll find it very, very common with other deep learning papers too. So what are the pruning and quantization protocol? There's sparsity parameter T, which indicates whether, so this T basically indicates if T is 0.9, which means that 90% of model weights are removed over the course of training, leaving a maximum of 10% non-zero weights at inference time. Basically, it's a parameter they're using to quantize. What did they do using that? So basically, they are pruning between steps. So if you notice, I wrote they did it 10,000 steps they went over. So their pruning was done every 500 steps between 1,000 and 9,000. So that is what they're doing. That's how they're doing pruning. So they're explaining a little more about how they're doing pruning. And they're also doing post-training quantization with fixed 8-bit and dynamic range. And one more thing they explained here was MLIR, which is like a machine learning, I guess, intermediate representation, which is by TensorFlow Lite. Via TensorFlow Lite, they're using this. That's how they're pruning, and that's how they're quantizing. So yeah, I mean, this is just a very basic question, but let us look into the result, which is sort of very interesting to us. So if you look at the model, okay, now this is something which will be again common. It will be a lot of numbers in most papers, but don't get overwhelmed. Let us slowly look at it. Okay, so I was trying to see if I can maybe annotate on screen. It's okay. I can maybe.
Yeah, so you can actually click annotate in. Yeah, and then.
Yeah, and then, okay. Okay, let us look at the model part first. Okay, so if you look at the model part here, we have like a baseline model, which means that there is no pruning whatsoever. And then there is a compression, or like what they look into here again is something very interesting, is purely pruning for us. So it is 95% pure pruning that exists. They are actually pruning a lot of the model. That is another thing that we notice here. So 95% pruning is something they do. Okay, now let us look into the next section. So let us look into the part above, right? This part, the unitary and the intersectional attributes. So, sorry, it's just taking a longer time with this. So if you look at the unitary part, we have male, female or not male. So here they've given here male, not male, young, not young, which is what is given here: male, not male, young, not young. And then they're taking intersectional, which means male with young, which is what we are actually interested in, right? This is the one that we are actually interested in. I'll star it or something. Yeah, this is the one that we are actually interested in. This is what the paper is entirely based upon, is the young male attribute. But they're also doing intersection for other attributes. So I will leave this here, or okay. Yeah, I'll leave this here. Okay, let me now look into how they are doing it. So if you look into the error, right, error metric, they're using FPR, which is false positive rate, and they're also using FNR, which is false negative rate. Now, let us purely look into the baseline model as such. So don't look into the, model below. Let's just look into this part. Okay, so now the aggregate error that we get with a baseline model, which means you're not pruning it, it's just uncompressed, it's the way that you would normally run it, is they have like 5.3% error. Okay, and the false positive rate is 2.73 and false negative rate is 22%, which is good, right? Which means that the model is performing pretty well. Okay, now let us now compare it to what happens when pruning occurs. So what happens when pruning occurs? So something over here. So this is what happens when pruning occurs. So error over here, when pruning occurs, you can see the error rate immediately increases, which is also bad. And the false positive rate, there is a definite increase. So is the false negative rate, which shows the fact that, there is an increase in error which exists. So that's something that we immediately understand right out of the problem, right? Now, let us dig a little deep into the false positive rate, which is very interesting to us again. So, okay, let us only understand how false positive rate was done. So over here, we are looking at false positive rate. I hope I didn't erase it. But okay, so false positive rate for the aggregate, it was 12.72% is something we noticed from before. So now let us look at male. For male, it is 49.54%. So, 12.72, but how is it segregated between different classes? For male, it is 49.54, but for female, it's only 6.32. What does it mean? It means that the model is biased towards this here, right here, this here, versus here, which is 6.32. So this is a disproportionate, or this is a bias that we immediately catch, right? So that is something very important to us right here. Another thing, maybe something else that you can catch here in terms of intersectional attributes. Let me erase this so that you guys can also catch it. Can someone point out maybe something that they found out here? Let me see the chat. Did someone point out something? You can look at the numbers here. It's supposed to be 12.72.
Yeah, so Ranjo actually pointed out female young.
Yeah. Female young. Yes, exactly. Female young is actually low, but male old is actually very high again. So that's again very, very interesting, right? Because if male old is so high and female young is so low, which means the model looks more here than there. So again, what does that mean to us? That means the model is biased. So all of these things are only understood when we are looking at protected class attributes. Now imagine if the model would have been only trained on blonde hair or not. We wouldn't have looked into the, we wouldn't have looked into bias that exists in these compressed models. Soham, is there anything else that I missed in terms of the results?
No, but I mean the results for male and old is like it goes from 1% to 101%.
Exactly. That's another thing which is very interesting. Exactly. So if you look at this and this, it goes from 1.12% to 101%, which definitely means there's a bias that exists and the model is looking more at this than at this or this. So this versus this is still a little low, and this versus like this from this is not much of an error increase. So here is the entire, bias which exists. Sorry, I'm really bad at drawing, but yeah. So yeah, that is pretty much the gist. So, in case you do see results like this, do not get, a bit, what you call, overwhelmed, or become like, oh my God, these are too many numbers. Try and understand what's happening. And maybe you can get some, results from it or insights from it. And after all, we're all like data scientists or work with machine learning or aspire to work with machine learning, and numbers are something that we'll have to look into again and again. So don't get overwhelmed, and you are going to look over results like this probably a lot more times. So yeah, which brings me towards the end, because I do know that I have been using a lot of people's time. Oh, sorry, I'm supposed to remove this. Okay, so what does this establish as such? If we look at, given a CIE, it's obviously identifying a small sample. It's basically a human in the loop annotation tool. And CIEs are whether the predictive behavior, it's basically where it diverges from compressed model to, non-compressed models. And yeah, this on all, maybe I can go over sometime later because it's a bit of math. But yeah, you can go over the paper on it. So the conclusion is basically, even though the model is compressed and the overall error, as we have seen, is rather remains unchanged from, if you look at, it was like maybe a 5% error or something of the sort. And there is not much of an error difference when you look at the error as an aggregate. But when we look at the data and the protected set of attributes, we see that there's a disproportionate error that exists on these attributes as such, these protected set of attributes, and which means there is a bias that exists. This shows that, there are certain annotating points which diverges, which exactly means that CIE exists, which is the metric they talked about before. So hence they proposed the use of CIE as an attribute for agnostic human in the loop auditing tool. And yeah, what about other compression techniques? Something that the paper did not go over. So what are the ways the paper could have improved is another thing that you should be thinking. So I mean, as a person reading the paper, you should also be internally critiquing it, because it really helps you think beyond it, right? Do not like think this is whatever the person has written is absolutely right. It's something that they have come to a conclusion with a certain data that they had. What happens when the data changes? What happens when, for example, they applied pruning only on training? What happens when they apply it post training? So those are questions that probably should come to your head, and I mean, it's okay even if it doesn't, but do not stop yourself from questioning that, because that really helps you read a research paper well. It's about critiquing the paper too. So yeah, nevertheless, I think this brings us to the end. Do you guys have any questions for us? Guys, feel free to drop your questions in the Q&A section. Okay, then I know I have already gone 30 minutes over the time. So thank you so much for joining in. So I guess someone said kindly repeat. What do you want me to kindly repeat, Zen? You can let me know if you have any questions for me. Recommend similar papers. Yeah, sure. I can go ahead and recommend similar papers. I'll go ahead and drop it onto our Slack channel. I will, we have a few papers already that we're going to be talking about this week with Edge Impulse too. So do stay tuned and we will drop in the papers. Zen, if you have joined late, not to worry, we have recorded the session. So it'll be up on YouTube. And you can check out the YouTube link on Woman Who Code @YouTube. You'll find the link soon there. Okay, and done. Need papers related to robotics. I can try and find out, Chessie, if there are papers related to robotics. I'll go ahead and post those on the group too. If I don't, feel free to like remind me and ping me, and we will find out some papers for sure. And yeah, sorry.
Yeah, sorry. So what I was saying was, searching for papers is a skill on its own as well. And you could, try practicing that by going to Google Scholar and searching for papers that you are interested in.
Yep. And again, do the method, read the abstract, read the conclusion, figure out if it fits you. That's the only way to read a lot of papers at once. Do not go through the entire paper and overwhelm yourself with the content. And maybe a little off topic, what is the difference between pruning and dropouts?
Yeah, so I can take that.
Okay.
So pruning happens. So pruning is happens after you train. So the neurons or the connections that you removed, they stay removed. Whereas in dropout, we don't remove any of the like we do remove the neurons and like the connections, but we only do that during training, and then we keep the connections when we actually perform inference. Uh, yeah. So because we do not, because during pruning we do not keep some of the connections or some of the neurons, we get some performance savings because we don't have to calculate those values.
Why do you consider, what do you consider should not be included when pruning?
It's a good question. I'm not like sure. Like should not be considered. Let
So
me think.
maybe we can drop the answers on Slack. I know again we are moving a little over time here, so I really want to be, really, I really want to take into consideration everyone's time. So Jesse will drop that into the chat too. I'm making a note of it, and we'll drop both the robotics paper and that onto the Slack group too.
Mm-hmm.
Yeah, and one more question we had. When do you go looking for, when do you go looking for paper? Is it when you think you need something, or do you subscribe to a topic? So I think like that's a very interesting question. When do you need to go looking for papers? Obviously you can go looking for papers at work, or when your research is needed. That is definitely, which is sort of motivated by that. But one another thing you could probably do is look at papers, like follow people, as we said, on Twitter, and they usually tweet papers. And when they tweet papers and it's something that is a topic that interests us, we go ahead and read it. So that's the way that we do right now, if it doesn't directly impact our work, or is something just for casual reading. I hope that answers everyone's questions. Again, feel free to ask us questions on the Slack group. Until then, I hope we can see you on our next session. Bye guys, and I hope you have an amazing weekend. I hope everyone stays safe, and take care.
Bye.
Bye bye.